Good afternoon. My name is Raúl Monge, and I work as engineer in the Aragon Institute of Technology, Innova. I'm going to explain the methodology to identify noise vibration problems for rate quality improves. Well, this presentation is divided in 3 points. The first is introduction of general problems of noise and vibration that the user perceives. Then the second point is the identification of the noise and vibration problems. In this case, only I will explain the vibroacoustic characterization on leaf methodology, but the other methodologies are mentioned and I explain the procedure. And finally, a conclusion of different methodologies. Well, improved rate quality is an important objective of leaf manufacturers. The perception of the rate quality by user is based on noise, vibration, on noise level, vibration level, and performance inside the leaf car. The vibroacoustic analysis in the leaves can be made to determine causes of the absence of comfort inside the car. The main cause of the absence of comfort can be produced by noise and vibration source, such as machines or drives, hydraulic pumps, operator doors, electrical control cabinet, and sliding systems. But therefore, other causes that could be produced absence of comfort, such as resonance of components and insufficient isolation between the source and the receptor. Therefore, the passenger inside the car receives noise by airborne and structural transmission, vibration by structural transmission from the source, and bad performance from bad levels of jerk and vibration or acceleration. Okay. In this page, there are the 3 methodologies, but only I will explain the first. The vibroacoustic characterization of leaf methodology is used to evaluate the behavior of the leaf and find possible solutions based on vibroacoustic and dynamic measurements. In this methodology, I applied different techniques of analysis, vibration and acoustic, such as fast Fourier transform, sound equivalent level, octave band analysis, frequency response function, and operational model on operational deflection shapes. Based on the results of the different techniques and find or applying a correlation, it is possible to get insight to making programs. The source contribution to noise inside the car methodology identified and quantified the vibration and noise source by using frequency response and coherence function. In this case, we applied the multiple coherence and output power allocation techniques. And the panel view contribution to the noise inside the car methodology consists to estimation the contributions of the sound power of the panels to noise to the pressure level inside the car, based on velocity vibration panel. Then, I begin with the vibroacoustic characterization of leaf. In this case, it's necessary to measure the rate quality, vibration measurement on the machines, noise measurement inside the car and inside the hoseway, vibration transmission through the load cells of the car frame to car, and vibration measurement of the panels of the car, and finally, operational model analysis and operational deflection shape of different components of the installations. The measurements are made or are taken with different load conditions to analyze the effect of the load inside the car. And in some situations, it is necessary to measure with different nominal speed, because with this measurement, it is possible to analyze the effect of the frequency to the problem in this case. And finally, it's necessary to find out correlation between the different results. In this case, I will explain with a real case. The first measurement is the ride quality, and this measurement is valid to evaluate the behavior of the elevator installations during the trips with different loads. In this case, can be seen that the nominal speed, in this case is 0.85 meters per second, is lower than the nominal speed of the machine, 1 meter per second. It can be due to the error parameters in the inverter. And the noise inside the car is more or less 58 decibel or dBA. It's a noise level higher for this type of the installation because this is a low speed. But the rest of values are good values because the vibration in the car is good and the acceleration and gear are good values. Also, it's possible to analyze the spectra, the vibration spectra in narrow band spectra, on FFT analyze to the floor to determine is one peak of vibration influence in the comfort of the lift. In this case, can be that the performance of the lift, the machine have problems to achieve the nominal speed without load in car during downwards conditions, but with 100 kilograms in the car, inside the car, the nominal speed is achieved completely. This cause can be due to machine has not enough power, electrical power, error in counterweight load, or high friction force to a sliding between guide shoots and guide rails. And in this case, appears the vibration spectra on the floor. In this case, the vibration peaks from 0 to 8 years, no present peaks that influence in the comfort, but appear a peak at 162 years that can be influenced in the noise inside the car. The vibration measurements are made around the machine area, and we measure vibration near shaft bearing and through in vertical direction through the isolators, and then in the guide supports in horizontal direction. This measurement is used to evaluate the vibration severity of the machines. And the analysis to the spectra can be used to determine the frequency of the machines, rotational frequency, power supply frequency, bearings or resonance, and it is possible to determine if the machine have frequency relationship with the vibration in the floor car. In this case, I said before that the nominal speed is 0.85 meters per second, and in this case the electrical power, the power supply frequency, are 27.1 hertz, because the nominal at 1 meters per second is 31.9 hertz. In the spectra of the machine can be seen the different peaks. The more important, or the peaks analyzed, is the frequency peaks of power supply at 27.1 hertz, the 6 harmonic of the power supply, that is 162 hertz, and a peak at 70 hertz in horizontal direction, mainly, that could be of a pitch of the machines around the isolators. The vibration severity is higher in horizontal direction than in vertical direction. It could be because the low frequency of 70 Hz contribute to the values at the low frequency. Other measurements are the vibration transmissibility through the isolator. In this case, we applied the frequency response function between the frequency machine and the frequency machine frame or frame machine. In this case, the values are higher than 100%. In this case, the isolator, they are not working correctly because the values is higher than 100%. And in this case, if a problem in this installation, this can be the vibration and the transmissibility. Only analyze the main peaks of the machines. Then the vibration, the guide support, can be seen that the main peak is the 162 Hz. Therefore, this peak can be produced vibration of the wall of houseway, and they can be produced noise inside the shaft. The noise measurement are made inside the lift car and inside the houseway in 2 points. The 2 points are above roof of car and near to the machines. With the different measurement, we obtain the noise equivalent level, analyze the evolution during the trip, the noise evolution, analyze the noise spectra to determine if the noise problem are a peak frequency or are a broadband noise. And it's possible to determine contribution of the machine frequencies and converter frequencies by FFT analyze to the spectra of this band. And can be estimate the noise transmission because it's possible that the transmission was or are airborne or structural transmission. In this case, appears the spectra inside the car and near to the machine and near above the roof car. In this case, can be seen that the noise equivalent level, the levels near to the machines are higher than the noise levels inside the car. Therefore, there are higher level inside the houseway than inside the car. But in car appears the main peaks or the main band is 160 Hz, and this is the band that has more contribution to the noise equivalent level. Whereas in the houseway, the contribution between 125 and 5 kHz is similar. It's more broadband noise than the big noise in this case. Then we analyze the narrowband spectra of noise and can be seen inside the car and can be seen that appears a peak at 162 Hz. This is relationship with the 6 harmonic of frequency supply, electrical frequency supply. And the noise transmission from houseway to the car is obtained by deducting the levels above the car roof from the levels inside the car. In this case, if the levels are positive, is that the noise transmission are structural, but is lower than zero is airborne transmission. In this case, at 160 Hz is a structural transmission. Another measurement that we use made is the transmission through the load cell between car frame and car floor. In this case, with frequency response function. In this case, all load cells have a transmissibility lower than 100%, and all cells are working correctly. But it's possible to improve the load cell 3 and 4 for reduce the transmissibility. And the other measurement is from the previous is determine the vibration of the different panels. In this case, we divide in 4 panels. One panel is the floor, one panel is a roof, other panels is a keyboard, and the other panel is a lateral panel. In this case, we put accelerometers in the center of the panel and we measure the different vibration of the panels during the trip. And in this case, can be seen that the FFT spectra showed that the main vibration peaks appear at 27 Hz and 162 Hz, es decir, at one of the frequency power supply and the 6 harmonic frequency power supply. In general, the maximum values appears in the roof car. And this is vibration can be produced noise, increasing the noise inside the car. The last measurement is to obtain the natural frequency of the different components. In this case, I can I can detect that the roof can be produce noise inside the car, and we selected 9 points inside in the roof car, and to determine the natural frequency around 160 Hz. In this case, appears a mode set at 166 Hz, and this mode may be self-excited by the 6th harmonic of the power supply frequency. In this case, can be seen the set of the experiment, and in this case, can be seen the model with LMS software to obtain the different model shapes. Also, the machine frame has a mode at 164 Hz, and therefore this mode may be excited by the 6th harmonic of power supply. In this case, we make the operational model analysis, and the shapes of the operational model analysis is muy similar to the operational deflection shapes during the running of the elevator. Then, with the different measurements explained, to improve the rate quality, I propose different actions. Review the correct loads in counterweight, reduce the friction force between the guides, review the machine trying to minimize the harmonic peaks, new design of the machine frame, new design of the isolation of machine frame, minimize of the noise of the level of source excitation, increase the damping of the roof panel or change its stiffness, and improve the isolation between the machine and the guide supports. The other methodologies only explain the procedure. The first is the source contribution vibration and noise to noise inside the car. This methodology consists to apply techniques of identification and quantification of noise and vibration source using frequency response and coherence function. In this case, the first point is selecting the receptor and source of vibration and noise, obtain the global contribution of the source selected to the noise inside the car by means of the multiple coherence, and obtain the contribution of each source to noise level inside the car by means of the calculation transfer matrix between each source and the receptor, by means application the output power allocation. Is the equation to multiple coherence. In this case, we apply the computational algorithm or matrix method, and this the equation to obtain the matrix transfer of the machine of the source. The interpretation method is an algebraic method. The individual contribution are combined, and the combining effect are quantified by a triangular matrix scalar. This technique for me, is complicated because the algorithm program and visualization is implemented manually in MATLAB software for each frequency to analyze. And the visualizations show that the contribution of the different inputs. In this case, in blue colors are each input, and red color is the contribution, the total contribution to the noise inside the car. In this case, there are sources that plus effect and other that contrarrest effect. And the last methodology is the panel contribution to noise inside the leaf car. In this case, we obtain the right noise transfer matrix by the transfer matrix by right noise software. Then, according to the sound power vibration standard ISO 7849, we calculate the power source, the sound power source, from the vibration in velocity speed. Then with the experimental data, vibration, velocity, speed during the trips, and pressure level, we can correlate the model to obtain the pressure in the leaves. And finally, and the conclusion is that the vibroacoustic characterization of leaves methodology enables us to discover how much the different source, vibration and noise, qualitative affect to the receptor. Therefore, it enables us to know which leaf component needs to change in order to improve the noise quality. However, the improve are estimated roughly. The source contribution and panel contribution methodologies permit to obtain quantitative results of the contribution to the source, but their application analysis are complex. Therefore, the first methodology is perfect for troubleshooting activities, whilst the other two are more advisable for research and development activities. Thank you for your attention.